Hello again. So in this session, I'm going to solve one example of Bernoulli equation so you see how you can use it in engineering problems. So let's get started. Here we have a nozzle. So a nozzle of water converges gradually as you can see in this figure. Assume the flow is approximately uniform, incompressible, steady, and inviscid. Also, gravitational effects are negligible. And the flow rate in the nozzle is given as Q. And the ambient atmospheric pressure as PA. Okay, so this is a problem statement. And now the problem wants to do this. A, drive. So let me see if I can bring this a little bit down. Drive an expression for the gauge pressure at a station where the area is AX. Okay. And B, show that the net X component, yeah, I think I need to still bring this further down. Okay. Show that the X component of force and the nozzle is given by this expression fx equals to rho q square times a1 minus a2 square over 2a1 a2. And what are a1 and a2? a1 is the area here, and a2 is the area here. And ax is just any arbitrary distance between these two. So this distance is ax. This distance is x. And the area of the nozzle here is ax. And I name this as a star. The location of it. Okay. And here section 2, and here is section 1. So this is how I name it. Okay. So let's get started. First, I'm going to start with A, solution. So answer. So A. So first we write the mass conservation for steady flows. So mass conservation for steady flows, and that is as follows. Mass in, so say we have this control volume from 1 and 2, okay? Say we have this control volume. So mass in into this control volume is what? Is rho V1 A1, okay? So this should equal to the mass out and also the mass here, this section. Okay, it should also equal to this one. So because of mass conservation in a steady flow, so it equals to rho Vx Ax and also equals to rho V2 A2, which is what? Which is the mass flux that goes out of this nozzle. So the mass that comes into the nozzle should equal to the mass that goes out of the nozzle. And because density is constant here, is for example for water, so I can say that V1A1 equals to the flow rate, the volume flow rate Q, which is constant, equals to Vx Ax. And so I can say that Vx, the velocity at here, point start, any arbitrary point, is going to be Q, the volume flow rate, over Ax, the area at that point. Okay, so this is mass conservation, and what we want here is the gauge pressure at this point. What is Px, Pgx, say? Right, we want to know what is this. So here we only have a relation for velocity. So in order to find the relation for pressure, I'm going to use Bernoulli equation. So apply Bernoulli but where? So we have to apply Bernoulli along a streamline. So along a streamline, flow streamline between, so the streamline that I am going to consider here is something, say for example from here, point star to section 2. So this is like, for example, you can assume this is a fluid particle that goes from star to point 2, station 2. So I'm going to write it between star and 2. Okay. So let's write it. So we have Bernoulli equation. I'm going to use the simpler one, the simpler form of that. I'm going to use this form. This is constant along this streamline. So what I can do is just write it for both of them. So the left hand side should equal to the right hand side of this. Okay. So we have rho Vx squared. So let me just make the changes here based on that. Rho Vx squared. And then we have Px. Px plus rho Gh equals to P equals to the velocity at the last point, which is gonna be 1/2 rho V2 squared plus P at point 2, but P at point 2, it's actually the atmospheric pressure, right? Because this is in the vicinity of the atmosphere. So what you get here is the ambient atmospheric pressure. So pressure at point 2, because here is in the vicinity of air, is gonna be just atmospheric pressure. So I can just write it as PA, as stated in the problem statement. Pressure, the atmospheric pressure is PA. Okay. And then plus rho GH2 again. But as the problem states, I can assume that the gravitational effects are negligible. So what does this entail is that these terms are 0 because gravitational effects are negligible. The same thing for this one. This is gonna be 0, almost 0. So what does this gives me? This gives me the following formula. So what is gauge pressure? Let's first see. So what is PGX? The gauge pressure is the difference between the absolute pressure, so it's PX, and the atmospheric pressure or ambient pressure, okay? So we, based on this equation, we see that gauge pressure, and this is what we wanted to get, equals to 1/2 rho V2 squared minus Vx squared. Therefore, Pgx, which is what we wanted to find in the first part of the problem, so we can write V's as Q over A, okay? And this is going to be rho, instead of V squared, I'm going to write Q over A. So just factor Q squared. I'm going to get this 1 over A2 squared minus 1 over AX squared. Okay. Now the second part wants us to find the force that the fluid acts and applies and exerts on the nozzle, the x component of that force. So in order to do that, what we need to do is to integrate. So let me just let me first show it, and then I will explain how we can do it. So say we are looking at this star point, some arbitrary point, and I want to show what is the force that is applied on the fluid on the nozzle here. So we have some section like this, the x component of it, and we have the here it is. Okay. And then we have a pressure force that acts perpendicular to this small element. So I can write this as, say, let me make it a little bit larger. And then this one is this. So this is dFp, the pressure force, but for a small element, say that we have assumed here. Okay. And here we have, I want to calculate the force along for this element, for this area, okay? So this is dFp, and this is the area of this is ds. I'm just going to call it ds. Okay. And then here we have theta. The angle is theta. And let me show it here. And also this angle is theta 2. Okay. So I want to see what is the FP in the x direction, the force of the pressure in the x direction. So it's going to be what? It's going to be dFp, the total force, times sine of theta. So let me show it here, why it's sine of theta. So here it has two components. One is going to be this part, and then one vertical component. So this part, which is dFpx, is actually dFp times sine theta, right? So it's going to be dFp times sine theta. Okay. And what does this equal to? So for dFp, the pressure force we know along that is going to be the gauge pressure, because I just want to know the gauge pressure, because the atmospheric pressure is everywhere. So we always work with the gauge pressure. So because the atmospheric pressure is applied both here, this side, and inside and outside of the nozzle, so we just remove that from everywhere, because that's everywhere, right? So we only look at how much the difference is between the atmospheric pressure and the pressure of the fluid, so it's going to be the gauge pressure. So that's why I write P1G, the gauge pressure, times the area, ds. Okay, so ds is area, the surface. So this is the force, and then you multiply this by sine theta. Okay. And what is sine theta? So remember, this is AX, right? Sine theta is how much ds sine theta. Let's see what is this, ds sine theta. So if we name this dA, why this is dA? This is how much A is gonna grow if we go this way, right? This is delta A. This is how much A has grown as you go, is increased as you go from right to left. So I can just write this ds sine theta, as you see here, is just that area, which is dA. Okay. So this is how I can write it again. So this equals to it's everything. So this equals to P1G times dA. Okay. So if I want to get the total force in the x direction, pressure force in the x direction, what I need to do is, if this is point 2, section 2, say, okay, here, I need to take an integral from point 2 to point 1. So integral from 2 to 1 to get the total force on the fluid, on the nozzle. So FPX, so let me, before I will write it, integrate the pressure along the nozzle to obtain the x component of the pressure force. Okay, so it's going to be FPX equals to the integral from point 2 to point 1 of this dFPX that we define, which is going to be the integral from 2 to 1 of P1G gauge pressure. Why I write it as P1? It's just PG. So this is just PG X, right? Sorry about that. It's just PGX. So PGX times dA okay, so you take that integral and let's see what is this integral. We have PGX here, so we just substitute it into the integral. So it's gonna be what? It's gonna be the rho q squared over 2 is constant, so we can take it out of the integral. So rho q squared over 2 is constant, so it's gonna be integral from 2 to 1 of 1 over a2 squared minus 1 over a squared dA. Okay, So now let's take this integral. So the first term of the integral, which is this one, is constant. It's just a constant number, right? A2 squared. So the integral of that is going to be that constant times a. And a varies from a2 to a1. So this is going to be equal to 1 over a2 squared a1 minus a2. Okay, so this is the first term. Let me see if I can, bring everything up. And now the second term is the integral is gonna be, if you take the integral of 1a over a is 2 squared, so it's a minus 2, so the integral of that is gonna be minus a to the power minus 1, right? So I'm just gonna use that, so it's gonna be 1 over a, the integral is gonna be 1 over a, and then we have a2 to a1 again, a1 to a2, so it's gonna be 1 over a1 minus 1 over a2, which equals to a2 minus a1 over a1 times a2. Okay, so if you add these two terms together, what we are gonna get? We are gonna get, I am gonna factor out a1 minus a2 over a2 from both sides, these two terms, right? This one and this one. And then the first term is gonna be a1 minus a2. Let me just make sure I'm not wrong. So this one has a square here. So it's gonna be 1 over a2. And then the second term, which is this one, we are gonna have minus 1 over a1, which equals to a1 minus a2. If you take the a1 times a2 square, it's gonna be a1 minus a2 times square. Okay, so the total force Fpx is gonna be rho q squared over 2 a1 minus a2 squared over a1 a2 squared. This is our final Fpx, the pressure force in the x direction. And just look at it here. It matches well with this expression that the problem wanted us to derive. Okay, so let me briefly review what we did today. So today we derived a simpler form of momentum equation, special form of that, which describes the dynamics of the flow. And it's valid in these conditions when the flow is invested constant, it has a constant density, it's steady, and it's irrotational. Then by defining a potential function, we were able to show this is valid. And then if you take this, if you take an integral over the streamline of the flow for this gradient, dot dl, you can show that this expression is valid, which is what we call as the Bernoulli equation. Okay, so this is kind of the Bernoulli equation, and then we showed some other interpretations of that, like it's the sum of the kinetic energy and potential energy, and when there is no energy loss due to viscosity, this should be constant. Then we defined the concept of stagnation pressure, where the velocity becomes 0. Then we have this stagnation pressure, which is kind of the maximum pressure. And then we non-dimensionalize this Bernoulli equation by 1 rho v square to get some non-dimensional numbers. So first one was speed ratio, the second one was the pressure ratio between the static and dynamic, and then the last one was Williams number or Freud number, which is kind of similar, which is kind of not similar, but the is 1 over, to be accurate, it's 1 over Freud number square. And then we solved an example that we had for this nozzle to find both the pressure force in the x component and also find the gauge pressure using both Bernoulli equation and momentum equation and mass conservation equations, right? So this is what we did in today's lecture. Okay, so in the next lecture, I'm going to look at some breaking waves and also start looking at some shallow water equations and open channel flows, which are other simplifications of Navier-Stokes, the Euler's equation.